not moving up. As network connection issues? Oh, okay.
Mm.
Because, okay, hold on. Okay, no, okay, we good.
All right.
Yeah. Professor, can you hear us? Can you hear me?
Yeah.
Okay, cool.
Okay, sounds good.
So, okay, good morning, everyone. Thank you for taking the time to attend my qualifying exam. My name is Cheng-Wei Ching. I'm third year PhD student from Professor Hu's lab. And first of all, I want to share my sincere gratitude to committee members for their support, their guidance throughout my full PhD studies over the past 3 years. And second of all, I want to introduce the committee members today. Professor Chen, he is a full professor at UCSC, and he serves as the chair for the committee. And Professor Chen Dong, he is an associate professor from Colorado School of Mines. And Professor Hailu Xu, he is an assistant professor from California State University, Long Beach campus. And the last member is my advisor, Professor Li Hu, and she is an assistant professor from UCSC. And yeah, I really appreciate that the committee members' patience with the scheduling challenges, and I'm so grateful that we could be here today after a few twists and turns. Yeah. So if everybody's ready, or Professor Chen, is there something you want to say?
Yeah.
Yeah.
Can you share your slides? Do you have slides to share?
Oh yeah, sure. Yeah, I'm if everybody's ready,
I think if everyone's okay, we just let Cheng-Wei to start the presentation, and we may ask a couple of clarification questions during his presentation.
Yeah, sure.
But if you have long questions, I would be grateful if you can save that for at the end of his presentation. All right. Yes, please go ahead. Please.
Okay, cool. No. Oh, okay, everybody see that on my slide? Okay, cool. The title for my presentation is Designing Efficient and Scalable Machine Learning System for the Age. And before we get everything started, let's go through the outline of my presentation today. First of all, we are going to talk about what a machine learning system does, and then we classify machine learning system into different classes based on their properties, based on their characteristics. And after all of that, I am going to introduce my project. It's Totoro, and it's a scalable federated system for machine learning training. And my second project is Basics, and it's a totally different trajectory compared to the first project. It's about a machine learning inference scheduler. And after all of the two projects, I'm going to discuss the future and ongoing project for the rest of my PhD studies. Okay. Then what does the machine learning system do? We use this example to illustrate how what machine learning system does. Suppose we have an application, and this application gives us the images of an intersection or a highway or a ramp. Then what we are going to do is, okay, tell me how many vehicles in this image. If we are training a model, then of course we have to go through the process like data processing, model selection, model training, and output. We are hoping the output give us a model with good accuracy performance. And if we focus on the machine learning inference, of course, we have to go through a few same process: data processing, model selection, model inference. Then our output we are hoping for is that the image we bounding box tells us that where the vehicles are and how many vehicles in this image. It's direct results compared to the machine learning training. Then a machine learning system focus on these 6 major operations like data processing, model selection, model training, and model inference. But most of the time, the focus of machine learning system is model training and model inference, these 2 operations. Because these 2 operations require sophisticated task scheduling, resource allocations. Then after going through what machine learning system does, let's classify a machine learning system into small category. Of course, we have 2 branches below the machine learning system. One branch is training, the other branch is inference. Let's focus on the training branch first. Basically, we have 2 major ways to realize parallelism, broadly speaking. For example, model parallelism and data parallelism. If we switch to model inference, broadly speaking, we can have 3 ways to realize parallelism, like request level, batch level, operator level. Then what did my first project do? Of course, it's a machine learning system. Then the first project I went for model training. And among these 2 ways of parallelism, I went for data parallelism, especially the federated learning system. So my first project is about designing a scalable federated engine for the edge, and it's called Totoro. And the reason that I went for this trajectory, the training and data parallelism, is that, well, because I have done some work on federated learning algorithm design during my master's studies. That's the first reason. And the second reason is that this project was in its early stage when I joined Professor Hu's lab. And Professor Hu asked me if I would be interested in getting involved in this super cool project. I say, yes, sure, it sounds amazing. And for the other part, and for my second project, I went for a totally different trajectory compared to the first project. I went for model inference, and among these 3 parallelisms, I selected request level parallelism. Okay, and the reason I make this decision is because I want to try something different. I want to do a work other than training, and I want to explore new possibility in model inference. And among the reason that I selected request level parallelism is that I think this request level parallelism is more general to many machine learning inference applications. So, following this insight, I propose Pixix, a black box scheduler for machine learning serving at the edge. And this project is still in preparation, and we plan to make the submission by the end of the summer. Okay. Now, before we dive into my first project, let's go through the background of machine learning at the edge. First of all, we have millions of edge nodes and devices, such as glasses, drones, wearable devices, or watches, even a self-driving car. They could be considered one kind of edge node too. And we also have in an edge cloud located so close to edge nodes to provide some entry-level computing resources, entry-level data storage, any kind of purpose for computation and storage. To realize these applications, to realize this scenario, there will be thousands of diverse federated applications running on the backend in the cloud, actually. For example, fitness tracking, traffic analysis, health monitor for different applications at the same time. And to run this application, the first thing they will do is that on the edge node, download the global model from the edge cloud. And the second, the edge nodes runs on-device training using the local dataset. And after the training, this edge node upload the local model to the edge cloud for model aggregation or for the next round model checking, things like that, for to continue the later further learning process. Then what's the benefit of this scenario? Well, first of all, because instead of relying on edge cloud to do centralized training, the training overhead is evenly distributed across so many edge nodes. That's the first benefit. And the second benefit is the low bandwidth usage, because instead of transmitting the raw data all the way up to the edge cloud, the data transmitted between edge node and edge cloud are models itself, which is considered lightweight, more lightweight than the data, the raw data itself. Okay, then what am I going to achieve in my system? First of all, I want to propose a system that is highly scalable to thousands of concurrently running applications and millions of edge nodes at the same time. That's the first goal. And the second goal is I want to provide ability to customize for diverse requirements for different thousands of federal learning applications at the same time. Lastly, I want to highlight adaptivity to edge dynamics, because edge nodes are usually considered resource constrained, and edge networks have a lot of unreliable links most of the time. But what's the challenge if I want to achieve my goal? Achieve my 3 goals I just mentioned in the previous slide. First is how to scale to number of applications and edge nodes. We are talking about millions of edge nodes, edge devices, running thousands of federal learning applications with diverse policies. Then what is diverse policies? Let's take a look at this example. Suppose we have 3 applications, and each application may require different participation policies, such as fair participation, random participation, cherry-pick participation. The second requirement is that maybe it's likely 3 different applications require different way to aggregate the global model in different way, like asynchrony or synchrony, semi-synchronization. And lastly is these 3 applications require different way to reduce the data size, reduce the data size of global model transmitted between edge nodes and edge clouds. So in conclusion, we must deal with many edge nodes that train many applications with diverse policies. That's the first challenge. Then what's the second challenge? Well, because we are focused on the edge environment, including so many edge nodes, and these edge nodes are typically characterized by varying bandwidth, unreliable links, high churns, workload surge. So we must consider a time varying and unpredictable environment. So that's the second change. Then let's move on to why the state-of-the-art federal learning system cannot achieve my goals. Okay. So typically, a state-of-the-art federal learning system employ 1 or a few perimeter servers. Whenever federal learning applications come in, the model for different applications are coordinated by 1 coordinator instance, where this coordinator also coordinates a lot of selectors that are connected to thousands, millions of edge nodes at the same time. More than that, coordinator creates master aggregator, which creates so many aggregators for model aggregations. Whenever an edge node finishes local training and wanting to upload local model to the system, the selector reports the results to the aggregator for model aggregation. This is the whole process of the state-of-the-art federated system run federating applications. Then what's the limitation of this architecture? Well, first of all, we can see that there's scalability issues where because many applications rely on one or a few coordinated instances. The second limitation is customizability because so many federated applications require diverse requirements like participation, data compression, any policies for different applications have to be implemented on one or a few parameter servers. And the last limitation is because the static methods to span the number of aggregators and the number of selectors may fail to adapt to the time-varying environments like edge nodes, the number of edge nodes, the availability of edge nodes. So how do we solve these issues? How do we solve these limitations? So we propose Totoro, and Totoro is a scalable federating system, and it has two core concepts to solve the limitations of previous federating system. First of all, Totoro decouple a centralized architecture to a fully centralized architecture. And how we are going to do is that instead of relying on one or a few parameter servers for all federated applications, we assign an individual parameter server for an application itself. That's how we call fully decentralized architecture. And the second concept is we employ a self-adaptive path planning model. In this example, we can see, suppose we have 4 selectors and 2 aggregators and 1 master aggregators. And we can see the data flow from below to the master aggregator. And suppose there's one aggregator become resource limited. The selectors that have to relay message through the resource limited aggregator autonomously switch to a new node for message relay. That's the basically 2 core concepts in the Totoro design. Now let's move on to the architecture of Totoro. So Totoro basically have 3 layers, and we are getting to each layer in detail. The first layer is locality-aware peer-to-peer multi-ring structure. In this layer, for an edge physical network like this, we have a lot of edge nodes across the world. And what we are going to do is we organize a DHT-based peer-to-peer ring overlay for all nodes in this edge physical network. More specifically, we assign an individual and unique node ID to each node. So in this example, we can see this node's ID is 103220. At the same time, we initialize 3 data sets for this node to know what neighbors they have in this ring overlay, which is routing table, diff set, and neighborhood set. And the second step is, on top of the DHT peer-to-peer overlay, we divide the ring overlay into multiple rings based on the edge zone. So we call it multi-ring because we have multiple rings representing different edge zones. And the second, we propose a 2-layer routing. The first layer is for the routing on top of the multi-ring, and the second routing table is within the zone. By using this mechanism, we can ensure that the number of the message from a random node in the overlay to the other random node in the same overlay travels at most number of zones times big O of log number of nodes in the overlay hops to reach the destination node. So that's the first layer for the total design. And the second layer, we propose a publish subscribe based forest abstraction, and we use an example to illustrate how this works. Suppose we have an application one, and first we get the hash value of the application. Suppose this application is 77. Then what we are going to do next is to get to see which node has the numerically closest ID to the application ID. So in this example, we can see node 78 becomes the master for application 1 because a hash value of application 1 is 77. So node 78 becomes the master for the application. The second step, what we're going to do is that the workers for the application send a join message towards the master so to subscribe to the application. So in this example, we can see the workers for the application 1 is node 49, node 47, node 50. And the routing path from worker to the master form a data flow tree, just like what we can see here. So for the application 1, we can see the data flow tree, and we can see, for example, like node 47, node 49, and they send message to node 69, and finally reach the master node 78. And after creating this data flow tree, the next thing we will do is that the master broadcasts the model to all the workers along with the data flow tree. And then when the workers finish local training, they send the gradient updates or any model updates all the way up to the master along the data flow tree. And different data flow tree is for different applications. And we called it publish subscribe based forest, composed of different data flow tree for different application. But there's an issue if we only stick to these DHT-based routing mechanisms. Well, because edge networks are characterized by resource-constrained node, varying bandwidth, or unstable availability. So in this case, let's look at the data flow tree for application 1. Suppose node 69 becomes resource-constrained node, it's gonna cause the problem like straggler effect and long training time, because node 69 has to relay the message from node 47 and node 49 to reach the master. So we are going to solve these issues because we are using this mechanism in edge networks and edge environments. But what's the challenge we might have? The first challenge is, unfortunately, we don't have the global view of which node is available, which node has more resource, because for some security or privacy issues. And the second challenge is resources are time varying. For example, maybe now the node is resource rich, and the next second it becomes resource constrained. So what we are going to do is we propose a solution. It's called bandit-based distributed hop-by-hop algorithm. So the bandit algorithm is like a smart scale that tells us, okay, when we should try a new node to relay the message, then when we should use the best node we have known so far. So let's take a look at this example. Suppose we have a data flow tree for application 1, and let's focus on node 47 and node 49 now. For this node, they keep trying different different hops to relay their message all the way up to the master when they have message to relay, when they have message to send. So we can see for node 47, it has 2 candidates to relay the message, which is node 69, node 29, and at the same time, each node keeps track of how long it takes to relay the message. So for example, from node 47's perspective, I can see, okay, node 69 takes 6 seconds to relay my message, and node 29 takes 7 seconds to relay my message. And then node 49 do the same. Then whenever, for example, node 69 becomes a straggler, then the node 47 and node 49 detects that, okay, it takes more time, it takes node 69 more time to relay the message. So the node 47 and node 49 switch to a different node based on their previous history data. And this is how a bandit-based path planning model does in total row design. So now we move on to the performance evaluation. And first of all, we focus on the scalability. And in this experiment, we train 20 models simultaneously. And we evaluate and we use different model architecture for different data set. So from the left, we can see we use ResNet 34 for Google speech dataset. And from the right, we can see we use ShuffleNet V2 for feminist dataset. And what we focus on is how long it takes to have models converge in terms of accuracy. So the x-axis is total training time, and the y-axis is the accuracy. So first of all, we can see the total row has the model converge in a short period of time. And next, we compare the total performance to 2 very common open source framework, OpenFL and OpenFedScale. And we can see they have model converge in a long period of time, and it takes like around 180 hours for ShuffleNet V2 and 200 hours for ResNet 34. And this is because Total Row leverage a fully decentralized architecture to have model being trained in parallel instead of relying on 1 or 2 instances of parameter servers or coordinators. And next, we focus on communication efficiency. Recall that Total Row has 2 parts of communication. The first part is model dissemination. For a data flow tree, the master has to broadcast the model all the way down to all the workers along the data flow tree. And the other part is gradient aggregation, where after the worker finish local training, they have to upload the aggregation all the way up to the master along the data flow tree. Then we can see that even though the number of nodes inside a data flow tree increase exponentially by a 2-factor, the gradient aggregation time and model dissemination time increase linearly. And that's because we are using the DHT-based mechanism to ensure that the height of each data flow tree is at most big O of log number of nodes in the overlay. And that's all my first project. And now we are switching to a different trajectory, totally different trajectory from training to model inference. And it is called Pixie, a black box scheduler for machine learning ADH. Okay. Before we dive into the second project, let's go through the background of machine learning serving ADH. We use this example to illustrate how machine learning request is generated, how machine learning inference request is served. Suppose we have a few self-driving cars down the road, and each self-driving car is connected to like traffic light, satellites, a power grid or phones. And this self-driving car rely heavily on machine learning assist application. For example, a self-driving car may have this request: how bad the traffic it is in the next ramp. And this request has to be responded in a very short period of time. Why? Because this self-driving car maybe is approaching the ramp. Maybe this self-driving car is get off the highway. So this self-driving car has to know exactly what is happening in the next ramp very, very quick. And this request will be served in one of the edge zone that is located so close to the self-driving car. Let's say edge zone B serve this request, and the results include like a number of cars, like 200 plus, and the state of traffic is congested. And this edge zone respond to the request in 100 milliseconds. Now, what's the benefit of this scenario? First, we can expect low response time because edge zones are usually considered located very close to the client. And the second benefit is low bandwidth usage, because instead of sending the data all the way back to the cloud, back to the backend processor, the edge zone, the edge nodes can process the request and return the results to the clients quickly without sending back the data to the back. Okay, then what's my goal? What am I going to achieve in this scenario? From high level, what am I going to do is I want to build up an intermediate layer on top of different edge zones organized by different providers, different edge providers that can accept requests from the client, and this intermediate layer determine, okay, which edge zone, which edge provider has to serve this request. At the same time, this layer has to make sure that, okay, the latency LSO, for example, in previous example is 200 milliseconds, has to be met as many as possible. Suppose we have 10 requests, we want 10 requests to be their latency LSO as many as possible. And the last thing is we want to make sure the load balancing among many edge zones, among many edge providers, to make sure that the resource utilization is not ignored. As that's three goals we want to achieve in my next project. Okay, then what's the challenge if I want to achieve this goal in this scenario? The first one is opacity between edge servers and edge providers, because different edge zones may be owned or administrated by different edge providers, such as AWS or Azure from Microsoft. They may not be willing to share information about resource usage or workloads for security reasons, for privacy reasons. However, the current schedulers for machine learning inference requests extremely rely on this information. So that's why we have to realize black box scheduling across edge providers. So we, by black box, we mean the scheduling without using any information of resource usage or workloads. Then second challenge is the heterogeneity of edge servers and inference requests. I list the specification of three kind of edge nodes we have in our lab. We have a Jackson Orion NX, Jackson Orion Nano, and Raspberry Pi 4. From this table, we can see each device has totally different number of GPU, totally different number of CPUs, and totally different amount of memory. On top of that, the inference requests are heterogeneous too. For example, we have two very common applications. For example, the voice assistant applications. These applications leverage BERT space to be the model architecture to do the inference, and it's a large language model, so it has a lot of parameters. This BERT-based model has 28 million parameters. Instead, the traffic analysis applications only use two models, very tiny models. For example, TinyYOLO3 has 8 million parameters. Shuffle face name has 4.5 million meters. But the thing is, because these two applications are not always time critical, so for traffic analysis application, it has to be responded within 400 milliseconds because it's considered more time critical. And for voice assistant applications, it only needs 1,000 milliseconds because it's considered not very time critical. Okay. So what we are going to do is we must deal with massive edge heterogeneity if we want to achieve our goal. Then now let's take a look at why the state-of-the-art machine learning serving system cannot meet my goal. First of all, suppose we have a few inference requests coming in. Let's focus on this one inference request. This request has latency SO of 500 milliseconds, and the data size is 160, which means for this application, it has 160 image to infer. And the first step the machine learning system do is to check out the profiling data in the provider. And for example, this requires use a pink model and the blue model. So we can see the data size and the transfer time and the per batch latency on CPU for different models. Then to find out the best configurations, what the machine learning system will do is to, let's see which configuration is better. So based on this math, we can see, okay, we use batch size 8 because we can get a number of batches 20, which is because 160 divided by 8 is 20. Then the latency is, we can get is 20 times 16.5 plus 20 times 4.7 for different models. So the total latency, total estimate latency is 444 milliseconds. So now we have make decisions on the configuration for this request, which is 8 batch size, 20 batch size. Then based on the configuration, we can estimate the required resources, which is 95 times 3 plus 19 times 20. Then the scheduler in the machine learning system may use different algorithms, like heuristic, greedy, shortest queue first, or self-adaptive algorithm. Regardless which algorithm they are using, they're relying on one thing from the resource manager, which is provide system states for algorithm to make decisions. Well, in this example, we can see, okay, worker nodes number 2 has very rich idle resources in GPU, CPU, memory, and it has very short queue length and high bandwidth. So based on this resource stats, the scheduler makes final decision to dispatch the request to worker node 2 because it has more resource, because it has fewer requests in queue. So what's the limitation of this architecture? First of all, is it unpredictability? Because we may not be able to know, okay, what kind of CPU we are using. Because different edge provider may not share the CPU series, the GPU series. So that's the first limitation. And by the way, this table is from an OSDI paper, so it's pretty accurate. And the second limitation is the invisible resource usage and workloads. Because the edge provider may not be willing to share this information with other edge providers. So there's two limitations of this architecture of this state-of-the-art machine learning system. So what am I going to do is to propose a black box scheduler without using any resource information, without any workloads things that has to do with security or privacy issues. So there are two concepts in PIC design. First, I use a bandit-based approach to learning the completion latencies. Let's use an example to illustrate how it goes. Suppose we have 3 requests, and we send these 3 requests to different zones, and we get the latency results, for example, 250 for zone 1, 120 for zone 2, 300 for zone 3. Then we use UCB model to convert the result into a statistical model. And this statistical model tells us that the average latency and the confidence. And the confidence represents the uncertainty towards the average latency. So the insight is, okay, if a zone contains more requests, the more accurate is the average latency, because we will be more certain about the average latency. If we try a zone multiple times, we can see that, okay, the average latency represents more the real completion latency of one zone. So that's why the upper confidence gets lower and smaller and smaller if we try zones multiple times. So that's a core concept. Yeah, that's the first core concept in the PIC design. And the second concept is that we leverage a Lyapunov-based approach to ensuring load balancing. Suppose we have 10 requests in the queue, and we have 2 zones available to process these 10 requests. Then initially we assign 5 requests to each zone fairly, equally. Then we will observe, okay, how many requests are completed under SLO. Suppose zone 1 finished requests, only finished 3 requests under SLO, and zone 2 finished 5 requests under SLO. We can observe that, okay, maybe we assign too many requests to zone 1. Then for the next 10 requests, we change the load balancing rate from half and half to 30 and 70. So for the next 10 requests, we only assign 3 requests to zone 1 and 7 requests to zone 2. So the insight is we use SLO results to dynamically adjust the proportion of requested assigning to different zones. So that's the 2 basic core concepts in PIC design. So now let's move on to the main operations, like how the PIC runs if it has to make decision for a request. Suppose we have the 3 zones, and we know that average latency for different zone is 150, 200, and 250 for different zones. And what we know is include completed requested. So for example, zone 1 finished 10 requests, zone 2 finished 20. And the next, we initialize the load balancing rate fairly and equally to 3 different zones. And let's suppose that there's a request with SLO 200 coming into the system, then we have to make decisions on which zone to take care of this request. So the first step, we normalize the average latency by SLO. So let's take a look at zone 1, because zone 1 has average latency 150, which is lower than 200. So we normalize the latency, so we give it a higher score for zone 1. So that's why it has a 0.25. The next step, we calculate a UCB, the upper confidence bound, using a UCB formulation. So based on the formulation, we first calculate the zone 1, the UCB for zone 1, and the 35 in here comes from the sum of the total completing request across 3 different zones. So it's 10 plus 20 plus 5, which equal 35. And the 10 is because zone 1 has finished 10 requests by far, so the final result is 0.56. And we can do the same for the the rest of two zones. And from this result, we can see zone 3 has higher upper confidence bounds. It is because zone 3 only finished 5 requests by far. And similarly, we can see zone 2 has the lowest upper confidence bound because it has completed 20 requests by far. And the next operation, we combine normalized latencies with upper confidence bounds. So for zone 1, we combine 0.25 and 0.56, which equal 0.81, so 81. And we do the same for the rest 2 zones. And next, we combine the scores with the low balancing indices. So for zone 1, we do we plus 0.81 and 0.33. So it's 1.14, and we do the same for the rest of 2 zones. And then finally, we use this final score to determine, okay, which zone is better for this request. So because zone 1 has the highest score, which is 1.14, so zone 1 gonna take care of this request in the end. And after that, after the zone 1 finishes the request, we update the data using the results. So for example, zone 1 couldn't finish this request under SLO, so we lower the low balance index from 0.33 to 0.30. And we increment the number of completed requests by 1 because he completed one more request, and we increase the average latency because based on the latency results. And that's the main operations of the PIC6 design to make scheduling decision. Okay, now let's move on to the performance evaluation. And first of all, I want to talk about the methodology for the experiment. To evaluate PIC6, I use 4 very common applications from different papers. The first one is smart traffic analysis, and the campus safety monitoring, and voice assistant, and checkbox. And from this chart, we can see different applications use different model, okay, and has different inputs. For example, the smart traffic analysis, it takes the image it takes the pictures and photos from intersections, and first it has to go through the SSD inception to do object detection to see how many objects in an intersection, and next to detect the car, the details of the car, it uses a Google name car to know which car is running on the road, and it uses shuffle face name to detect the human faces on the images, in the images. Yeah. Okay, and next, first we focus on the latency results, and we compare PIC6 against 4 schedulers, and on the left is the optimal scheduler. It means that this scheduler has 4 excess of resource and workload. So we call it optimal schedulers because it can always do the best scheduling decisions based on the global view, any necessary information it needs. And we also compare PIC6 to Ray. It's a default scheduler, and MBS and Orchestra. These 2 schedulers leverage bandit-based algorithm to make scheduling decisions. So we can see that even though for different number of inference requests coming in, we can see the PIC6 can only achieve the latency close to the optimal scheduler. And next, we move on to the finish rate results. By finish rates, I mean, for example, we have 2 requests coming in, and we only finish 1 request under SLO, then the finish rate is 50. Yeah, that's how we calculate finish rates. And we compare PIC6 to 4 scheduler as well. And from this result, we can see that PIC6 can always give the results close to the optimal scheduler. And the reason why the optimal scheduler is always 100 is because we use the performance of optimal scheduler as a standard to normalize to normalize the other schedulers' performance. Okay, that's the two major instrument results for Pick 6. Then, okay, let's do a small summary. We have gone through the first project, the total of variant learning for machine learning training using data parallelism. And we have gone through the Pick 6, a black box scheduler for machine learning inference. Then what am I going to do next is that the first project, I'm going to propose a new algorithm. So a new algorithm to replace the bandit-based algorithm in total. So, and we're gonna submit it to a journal based on the previous total results. Yeah, and the reason that I want to replace the original bandit model is that the original model doesn't consider the resource competition across edge nodes in terms of communications. And yeah, I'm planning to finish this project by summer. And the second project is to complete Pick 6 theoretical and experiment results. From theoretical point of view, I am going to provide the guarantees on latency SOOs, and how many requests can be completed under latency SOO, and load balancing properties guarantee. That's the first part. And the second part is I'm going to use more metrics to evaluate Pick 6 performance, like load balancing, or yes, things like that. And the last project is that's what I'm doing. That's what I'm doing right now. Is to engage in a new project for test overloading at the edge. I think this project is gonna base on the second project, and from the implementation side and from theoretical sides, yeah. And I'm planning to finish by early 2026. And yeah, that's my 3 ongoing projects and future work for the rest of my PhD study. And yeah, thank you for your participation. I really appreciate committee members for coming into my qualified exam after 3 terms. I really appreciate that, and every other student coming to my qualified exam. Thank you all. Thank you all. And let's get started Q&A section. Yeah.
All right, let's start ask questions for Cheng-Wei. We may start from the audience.
Okay, cool.
Is the general audience has any questions? So we have Yan here.
I don't have any question.
Yeah, so if not, our committee, committee members want to ask questions now, or they want ask closed door? They want to have closed door discussions without the general audience? Okay, Yan, could you please log out?
Yeah, sure.
Thank you. All right, so we don't have committee members here.
Hold on. So is Chen fine? Stay here.
Oh yeah, Chen, would you please be excused?